Welcome back to the next lecture in our course on classical differential geometry for physics students. We're going to start a short topic on spherical geometry. We reviewed planar geometry, and now let's talk about the geometry on the surface of a sphere. So here it is, and I tried to draw a sphere here with the usual spherical coordinates. There's the angle theta off the z-axis and the angle phi in the xy plane off of the x-axis, like that. And I label a point P by those two angles. The angle theta is particularly interesting, as we'll see. Okay, so the position of the point P is given by r of theta and phi. If my sphere has a radius r, then I just do the geometry and I write down its position as a function of theta and phi, and I think that's all very familiar to all of you. Okay, so the x component is sine theta, cosine phi. Okay, and the y component is sine theta, sine phi, and the z component is cosine phi. Like, for example, I can check that here. Look at the picture. Here's phi. The projection of P in the z direction is cosine phi. Okay, and then the other components I get by projecting down into the xy plane. That projection down always involves sine theta, sine theta, sine theta. Then I project through the angle phi into the x direction, okay, onto the x-axis or onto the y-axis, giving me a cosine phi and a sine phi, like that. Familiar stuff. Okay, now how do I label the point P? Well, at the point P, I have r of theta and phi, and at point P there's also a normal. Okay, and I make that normal by, I see that it's just along the radius, and I just normalize it. So I divide through by the radius, and there's a unit normal at the point P. Okay, the point of that is that then I can set up a orthogonal triad at the point P to label the directions and vectors in the tangent plane. Okay, so the tangent plane will be swept out by the derivative of r in the theta direction. Okay, imagine small deviations in theta, then I'll have a vector in the direction of increasing theta, and I've written that down here. Then I'll have, in addition, a vector in the direction of increasing phi that swivels around here. See this cap around here, the phi, the vector of variable phi is tangent to that cap. Okay. And I just look at the picture, and I verify that this is a orthogonal triad. It's not orthonormal. I've normalized the normal vector, but the other ones I don't bother normalizing. It's more convenient just to use them as they stand. Well, now of course I can simply verify that it's orthogonal by calculating these derivatives. Okay, make r sub theta the derivative of r in the theta direction. Do the same in the phi direction, and then just take the dot products and check that it's a triad which is orthogonal, Okay, and that's useful to do. Okay, and that's the kind of stuff we'll do in recitation class and in the homework sets, but not in the lectures. Well, first thing we want to know is, what are the geodesics on the sphere? We want to do some geometry on the sphere. Okay, so we want to know the analog of straight lines in Euclidean space, and those are going to be geodesics on the sphere. Well, we might consider first, to get the right idea, okay, go to the North Pole over here and consider the position of a point of variable theta but fixed phi. Okay. Okay. So if we look at that direction, right, I can be on. Imagine this as being the top of the sphere, and I can look in this direction and in this direction and calculate the tangents in those directions. Theta varying but phi fixed. Okay, we'll differentiate this fellow twice with respect to theta. Okay, and you'll get a simple answer. It's just sines and cosines, so it's easy to do. You get a minus r, and then a collection of sines and cosines, which reproduces r itself. Right? Because they're sines and cosines, so up to a sine plus or minus, the second derivative is going to reproduce what you originally had. So in fact, r theta is minus the radius times the normal, okay, times the normal unit vector. Okay, well, the important point about that is that r theta therefore has no projection in the tangent plane. Okay. Okay. Now we've discussed curves. We discussed curves in Euclidean space. Okay, and we label them their curvature by taking their second derivative with respect to arc length. Okay, well, theta is simply related to arc length because theta times r is the arc length of a bit of a curve shown here, right? If you go out, if p is shown here and the radius is r, then this distance here is just r times theta. So that's the arc length. And so up to factors of r, the derivative of the position with respect to theta is just the derivative with respect to arc length. We see that, so that's proportional to the curvature of the curve being r of variable theta but fixed phi. We see it has no projection in the tangent plane. Okay? Okay. So from the perspective of a bug or a person on the sphere, they see that curve, the curve of variable theta but fixed phi, as being as straight as possible. Okay? If they can only measure the components of a vector in the tangent plane, well, this curvature has no components in the tangent plane. They say that's as straight as possible. And therefore that's going to be our definition of geodesic. Well, we've discussed it already in the textbook, and I'm just reminding it to you here in a very casual sort of way. Okay, but anyway, it shows us that the geodesics on the sphere are the lines of variable theta, okay, and fixed phi. So any one of those lines I can classify it by noting that it has a position r on the sphere, okay, and it has a direction which is the tangent r theta. Okay, well those two vectors r and r theta determine a plane. Okay, right? They lie in a plane. I see that's a plane which goes through the center of the sphere. Okay, and so I learned that geodesics of the sphere are just the intersection of planes that pass through the origin and intersect the sphere. Now I've done that thinking of what's happening from the perspective of the North Pole, but that's just a choice I made. Every point on the spheres is equivalent to any other point on the sphere by the symmetries of the sphere. I can just rotate the sphere. If I did the same consideration over here or over here, well, there's no difference because I can just rotate those points onto the North Pole. So if I do a construction on the North Pole, I've really got the essence of the problem. Okay. If I was considering the general case of a curve on the sphere or on some curved surface here, so I'm denoting a curved surface with the blue lines, and then here's a special curve embedded in the surface. Okay, then I can look at its curvature. I can look at its derivative, second derivative with respect to its arc length. Okay, and so at this point here, that acceleration, that second derivative, will have a certain direction, which I call kappa. Here's r double prime, the second derivative with respect to arc length. It points at some arbitrary direction, right? Okay, this is just an arbitrary curve on the surface. I can change its character a lot, move kappa this way and that way, certainly. Okay, so in general, it points in the direction kappa, and then that curvature vector will have a projection in the normal direction, and it'll have a projection in the tangent plane. In the normal direction, I'll call the projection kappa sub n, naturally. Okay, that's going to play a big role in our discussion of how to embed surfaces into R3. And then it'll have a projection into the tangent plane, and I'll call that kappa sub g, g for geodesic, and that'll play an important role in our discussion of the intrinsic geometry of the surface. I read off from the picture, just by Pythagorean theorem, that kappa squared is kappa normal squared plus kappa g squared, just that those edges make the sides of a right triangle. So therefore I see, for example, let's say I want to choose a kappa as small as possible. Okay, what can I vary? Well, I can vary the direction of the curve embedded in the surface and arrange things so that kappa g is equal to 0. Okay, if I do that, you see, then I've reduced the kappa squared to as small as it can be, because kappa normal is what it inherits from the surface itself. Okay, the surface is curved. I can't make the curve more straight than that. But I can arrange the direction of the curve here at this point such that kappa g is equal to 0, and then R is as straight as possible. It is a geodesic on the surface. Again, we're just elaborating on our discussion on the sphere to motivate the critical defining equation for a geodesic, which is that a geodesic is a curve which has geodesic curvature of 0. Okay. And we'll develop this idea more thoroughly, and it's discussed in the supplemental lecture that we're following now, number 9. It's also discussed in the other supplemental lectures, and take a look at that, because we'll look at it from various different viewpoints, and you'll get comfortable to it. So I'm developing the idea of geodesic as the straightest possible line in the manifold. Now, there are other approaches to geodesics, which are to think about the minimization of the distance, between two nearby points on a manifold. Okay, and maybe you're more familiar with that idea. Okay, but we'll see that that the two ideas are equivalent if we state the concepts in a sufficiently precise way. The points have to be sufficiently nearby, and then the minimum distance is the same as straight as possible. That is kappa g equals 0. And for a lot of our purposes, it's handier, to think about it in this particular way. And so that's what my emphasis will be. Okay, it takes a little bit more machinery to think about distances on the surface. It depends on the metric. Okay, and there's more machinery there. So I'm going to come in from this perspective, and then later on, we'll see that it's the same as a minimum of distance, or a stationary point distance, actually. Okay, so back to the sphere. We've seen that the points of variable theta and fixed phi sweep out great circles. These are the geodesics on the sphere. And so I could imagine two geodesics on the sphere with an angle phi between them. They're both starting from the North Pole with an angle phi. Each geodesic is the intersection of a plane, through the origin and through the sphere, as we've already discussed. And so here I see the path of the geodesic as I come along here, and I come along here. I see that the geodesics don't maintain a constant distance between them. They deviate, of course, and in fact, until I get down to the equator, where the geodesics you see are parallel, where they have a maximal distance between them, then they start below the equator, start coming back together, and they intersect at the antipodal position, the South Pole. Well, of course, nothing special about North and South Pole. This is true for any point P and its antipodal image, P prime. And I see that there seems to be simple behavior in the distance between the two geodesics, and we'll want to understand that. Okay. So now that we know the geodesics on the sphere, we can form triangles and see the effects of curvature on the geometry of triangles. So here's a triangle on the sphere. I have three geodesics, one that goes through point AB, one that goes through points AC, and one that goes through the points CB. And I label the angles alpha, beta, and gamma in just that way. Okay, and so that's okay. And so here, for example, is a rendering of that. Okay, on an approximation to a sphere, a little white balloon here. Okay, and I see A, B, and C, and I see the geodesics. Okay, now because the geodesics are great circles that intersect, they intersect one another twice. If I have a geodesic triangle on this side of the sphere, I also have it on the other side of the sphere. Okay, and I've labeled things with primes, but it's clear from the symmetry of the problem that alpha prime is alpha. Okay, beta prime is beta, gamma prime is gamma. And for example, the properties of this triangle are the same as the properties of that triangle. So the first question I might ask is, what's the area of the triangle in terms of alpha, beta, and gamma? Okay, this is a kind of problem which we'll face on general surfaces, but if it's a sphere, I can do it by trickery. I don't have to know all that much about curvature and Gaussian geometry yet. I start off with a trick. I begin with what's called a double lune. I just take two great circles and look at how they occupy the sphere. So here's and I call it a double lune. Okay, so I have two geodesics, okay, and they intersect here with an angle of phi, and there's an area enclosed in it. And here it is. Okay, yeah, and so here it is on my approximation to a sphere, my little white balloon, okay, and the red area is the area between, okay, the two geodesics. I want to calculate that area. I see if I have a lune here, then of course the geodesics intersect at the North Pole, then they intersect at the South Pole, so I have an image of the lune on the other side of the sphere as well. That's why it's called a double lune, indicated like that. Okay, it's clear that the area of the double lune is 4 times phi, the opening angle, where phi ranges from 0 to pi. For example, if I took phi equals pi, then I cover the entire sphere, okay, and putting phi as pi here, I find that this area of the sphere is 4 pi, and that's correct. Okay, and then I just looking at the picture, I see that it's a linear problem, so that for general phi, then the area of the double lune is simply 4 phi. I fit to the cases phi equals 0 and phi equals pi. Okay, and then I linearly interpolate between them with a 4 phi, and that gives me the general area of a double lune. I don't have to do a real calculation for that, but heck, you could do it too. You know vector calculus. You can calculate the area of a lune just by doing a very easy double integral, and you're invited to do that where you are. Okay, well, with the double lune then, I can come back to my geodesic triangle, okay, and calculate its area in terms of the angles alpha, beta, and gamma. Here it is, okay, and here it is over here. Okay. Well, look at this picture. I see 3 double lunes, right? Here I have a double lune with an opening angle alpha. I have a double lune here with an opening angle gamma. I have a double lune here with an opening angle beta. Okay? And those double lunes cover the entire sphere with a bit of overcounting. Well, how much overcounting is that? Well, if I pick a point over here, okay, it's only covered by one of the double lunes, the double lune of beta. Okay, it's similarly over here and over here. Point here is covered by the double lune gamma. Point here or here is covered by the double lune alpha. However, I see therefore that any point inside delta is covered by all 3 of those double lunes. So if I add up the area of the three double lunes, I get more than the surface area of the sphere. I've double counted my triangle delta, and then by symmetry, I've double counted my triangle delta prime. Okay, so let's add it up then. The total area of the sphere is 4 pi. That's equal to the area of the 3 lunes. Okay, but I've triple counted points here and points in delta prime, so I have to remove twice the area of delta and twice the area of delta prime. That's it. Then I'm all set. The area of delta is the same as the area of delta prime. That's clear from the picture. They're just images of one another. And so I can solve for the area of the triangle. Okay. Now I've done this problem for a sphere of unit radius, and I can just restore the radius, the general radius, r, just by dimensional analysis. Okay. So now I'm on a sphere of radius r, and I learned that the area of this triangle is what I call the positive deficit of the internal angles. You see, it's the sum of the internal angles minus pi. If we have a triangle on R2 on a plane, of course, that's 0. Okay, that's 0, but not so on the sphere. Okay, and multiplying through by r squared here, I get an area. Okay, this is an area. It has the dimensions of length squared, and this is where the radius of the sphere will be. Okay, that's a more conventional way to write this thing. We'll learn later that the Gaussian curvature of a sphere is just 1 over its radius squared. Okay, and so I'll throw 1 over r squared onto this side and call that the Gaussian curvature, and then this is what I result. And this is an example of the Gauss Bonnet Theorem in a manifold of constant positive curvature. Okay, so here's what we derived. Curvature times area is equal to the angle deficit. Let's take a look at that. Let's take a look at that. Well, in general, we see that alpha plus beta plus gamma is going to be greater than pi for geodesic triangles on a sphere. That's not very surprising. Okay, it's something that's curved. It's curved as shown here. Okay, and that curvature is going to create that inequality. We see that the angular deficit determines the size of the triangle, the area of the triangle, and we see that the Gaussian curvature K sets the scale. Okay, so I can look at a particular case of all that, and I show that here because I want to look at both the situations where the triangle is big and the situation where the triangle is small. Okay, so here's this situation. A is at the North Pole, and then I have a geodesic that comes down to the equator, like this. It's perpendicular to the equator. We saw that in our pictures already. Okay, this is the North Pole. This is the North Pole's equator. So this is pi over 2. This is pi over 2. Okay, and then I have alpha, and alpha can range all the way up to 2 pi. So I see the delta, okay, can be as large as 2 pi in the case where I take alpha to be 2 pi. Well, that's just the area of the semisphere. Okay, just the top half of the sphere, and I get that going over here, setting k equals to 1 for a unit surface, a unit sphere. Delta is equal to this, and in this case, 2 of the angles sum to pi, canceling this fellow out, and the size of the area is just that leftover angle itself. Okay, so there's a big triangle on the sphere, and it has a large deficit. Okay, large about 2 pi beyond what one might have expected coming from Euclidean space. Now we can consider the other option of a very small triangle. So we take k times a delta to 0. Okay, k sets the scale. In that case, if I take a small triangle so that this left-hand side is small, then I see that the sum of the internal angles approaches pi. I get back to a Euclidean triangle. That's just a demonstration of the fact that the short distance geometry on the curved surface is Euclidean. Okay. Okay. And so this is an example of some further developments in the supplementary lecture 9 on page 17 and 18. Okay, which show that similar triangles are congruent on the sphere. That is, if I'm on a sphere of unit radius, and I know the internal angles, then you see I know the area. Okay. In the case of the Euclidean plane, of course, you have similarity. You can have large triangles and small triangles of the same angles, but on the sphere, it's different because the Gaussian curvature sets a scale. If you tell me the angles, in this case the sum of the 3 angles, then I'll tell you the area. So very different sorts of geometries. And it's something that we're going to be pursuing as we go further in the course. Okay, that's all for today. And next time, let's take a look at geodesic deviation on the sphere.